The extra 2 lines you just have to write, and you can get rid on this function level, test case level iterations also. For every test case, now we are bending our answer to be big of one time, big of one time. We have just initialized our sieve to be at class level. We have just initialized our sieve to be at class level. That is not test case level, it is class level. And we are getting its power to every test case. We are basically able to state how many prime numbers less than my 5 into 10 raised to the power 6, 4 into 10 raised to the power 6, 200, 300. We are going to state it, it's big of one time complexity. We can quickly compile our this particular versions of this particular code and see its correctness. It's indeed correct. And now we have done our submissions. Is it faster? Is it faster? Yes, man, it's indeed faster. It's taking 0 millisecond, and we beat everyone, and we beat runtime to be every lead code users with this particular optimizations, with this small. Hi guys, ShouPri here. Very good morning and happy weekend. I guess you guys are doing very well, and you guys have already started the DSA practice sheets that we have discussed in our last video to all of you. So now from today onwards, let's pick some of the topics and get it done. So that is of mathematics foundations. Let's pick some topics from the top. So I will create a detailed video, so we will not do very rushing. So we will go very step by step and understand for each lines what actually we are doing and what is the motto behind that to write for any single lines. What is the motto behind that, we will understand very in depth. So if you know the basics of how to basically find prime numbers, so on today's agenda we will majorly focus this count primes and this sieve of Eratosthenes. So both the problems is basically lying on the concept of sieve of Eratosthenes. We will understand the very in-depth template or the templates in very thoroughly, so that it's basically set to our brain. So what is actually sieve of Eratosthenes and what is the requirement of we are using such an algorithm, sieve of Eratosthenes, or a predefined algo. What is like a very common, what can I say, like find primes, like we can calculate prime numbers in runtimes, and why it is not going to be help in kind of a particular problem scenario, that we will understand what actually the benefits it is going to be provide us, right? Yeah, so now let's start on the very first problems in our DSA playlist, that is of count prime numbers. So how you can access the problems, I think you guys is already doing, but in case if anyone is not able to basically access the problems, you just have to copy the link and you can go to this your favorite browsers and paste the links, and it will basically open the problem window for you for sure, right? So on the very first problems, we have this count primes. So what actually these problems basically state us, so we have a given an integer n, we have to return the number of prime numbers that are strictly less than n. So although this problem tagged as a medium, but I feel so like it's an indeed medium problem until you know the sieve of Eratosthenes. Then it's for sure and medium problem. So what actually we have to return, given an integer n, return the number of prime numbers that are strictly less than n. So here you can see we have n equals to 10. So there are 4 prime numbers less than 10. So they are 2, 3, 5, 7, right? So they are 2, 3, 5, 7. So what is the count? There are 4. If n0, then 0, n1, 1. So the very first prime numbers, if you like remember your like second standard mathematics, then the prime numbers are start from 2, and from 2 onwards there are a certain conditions based on which we can say a number is prime or not, right? But 0 and 1 is not a prime, is not a prime numbers altogether, right? Yep. So on very first we will start with the very traditional way how we can find the prime numbers. So if you guys know, then I guess you guys can able to recall it. So what actually a prime number state. So if I can take a sticky note from here. So a prime number, what is the definitions of a prime number? Prime number is divisible by 1 and itself, right? So it should have only two divisors. It should have only 2 divisors, right? So that is actually the prime number. So you guys should be aware of this. Any number is divisible by 1. 1 can divise any number, and the number itself can divise that number, right? So a prime number, we will basically provide the crown of a number to be prime. when it is divisible by 1 and itself, right? So that is the definitions of prime number. Now can we basically write some algo to basically give it to a code term? What we just basically discussed, can we give it some code term of logic, so that like we will create a prime functions is basically take a number and it will return a boolean. So what actually it will going to state us that particular number is prime or not. And how we can check a number is prime or not? We'll basically check the divisor of that number, right? We can check the divisor of the number. Now there are one more things, right? So now, what are the range of the numbers we check for its divisor? Can I say it's basically in the range of, if I am checking with a counter, so my counter should iterate from 1 to that number within this number. I think so you guys are able to see it, or else I can a little big the font. So now I think you guys should be able to see it. So the divisor check we have to run in the range of 1 to num, because if I am checking the divisor of a number num, then it is not making a sense a number which is more than which these conditions, like if my counter is greater than my num, then is there any chance that my number is going to be completely divised by this counter? Any number which is greater than the number that we are checking, is that number can be a divisor? Nope. That is not possible. NP for sure, not possible. That is not possible by number theory. I think so you guys should relate. So the number, the counter, we have to check the number in the range of 1 to num. Now there is a slight basically in time complexity we can get a slight modification, slight improvement by doing these things, right? So what we are basically stating, we will start our for counter variable, for counter in range in the range of 1 to num plus 1, as Python is exclusive of the last index, right? And we will check if my num is divised by my counter equals to 0, right? Then we will increase the counter, like the count of divisor plus equals to 1, count of divisor plus equals to 1, and finally we will check. Finally, what is the check we have to basically put? If my count divisor count is greater than 2, right? Greater than 2, then we can return false. It is indeed not a prime. Else we can return a true. So that is outside of the if basically. So I'm not able to basically, it's not taking the indentations, but I guess you guys are getting it, right? So that is the high level things we are focusing on, right? So that actually our ideal prime number code should looks like what we just discussed. We just give a code versions of it, right? So now if I can just try to write, I can take one more node of color this. I can place it here. So what I am basically stating, so if you put some basic observation, very basic observations, can we decrease the size small? This should be fine, right? It's taking. So if I am going to check, let's consider 25, right? 25 is prime or not. So what we are doing, we are checking from 1 to 25, and we are basically checking if the counter is devise my number, right? So rather than doing this, is there symmetry? So how it is? So if I am going to write its divisors in kind of something like this, 1, when we are at 1, then if 1 is going to divise it, right, then what is the reminder we have to say? So what is the else part? When we are going to multiply it to get 25, it's 25 itself. So 1 plus 25 is 25. So when we are at 1, we are checking if it is divising it. If it is divising it, we are going to check. We are basically going to check if it is second part also divising. So like this way, you can see now when we are at 2. So is 2 divising it? Nope, 2 is not divising. So 3 divising? Yes, 3 No. 25 is also not divisible by 3 also. 4, no. 5, yes, yes, yes. So 5, not here. Here it is. Here it should be 25 only. So here. So 5 cross 5 is dividing 25. 5 cross 5 is dividing 25, right? So I am basically going to check its square root. Not previously I am iterating from 1 to n, right? If my n is 25, then I am iterating from 1 to 25. But now I am stating I will iterate from 1 to square root of my 25. So, and I am checking with symmetry. So if 1 is dividing, okay, 1 is dividing. So on the other part is by default dividing. The other part is by default dividing. So here we got, when we are checking at 1, we are basically consider 25 also. So my count divisor is going to be increment plus 2 here, Here 5 is dividing. So what is the next part? The next part is also 5. Here 1 is dividing. What is the next part? It's 25. It's different. It's not 1. But when we are at 5 is dividing. Then what is the next part? It's again 5. So we already considered 5. So only this case we are going to increment its plus 1, right? Our count divisor we are going to increment by plus 1. So how many divisors we found? It's 3. It is more than 2. So it is not a prime number. So 25 is not a prime. So in by chance, if you guys are not able to understand, I will take one more case, right? One more case. Let's consider a good case. Let's suppose 18, right? Because we have some good number of divisors we are going to see here. So for 18, 1 cross 18, yes, indeed. So our count divisors is going to get plus 2. Then for 2, yes, it's also indeed. 2 cross 9 is going to be 18. My count divisors is going to be plus 2. 3 cross 6, indeed. So my count divisors count is going to be increased by plus 2. So now we have discussed, we are going to iterate for its how far we are going to iterate of its square root. Square root of 18 is kind of 4 point something, right? 4 point something. So we will take its round up and we will going to consider its 5, right? So we are still in the boundary. So we have iterated 1, 2, 3. Then we are at 4. Is 4 is dividing 18? No, not man. 5. No. So we have done with our iterations. Do we able to count all my primes, all my divisors of 18? You can see indeed 118, 29, 36. These are the divisors of 18. So we are able to calculate all of those. So that is the beauty of these algorithms. What we have discussed in the very root, we are iterating from 1 to n, but here we are basically stating we are not going to iterate from 1 to n, we are going to iterate from 1 to square root of n. I guess it's bound to be going to be clear to you guys all. But if not, then I will highly suggest to go to a rewind of this particular video, particular sections of this video. You will definitely get the gist, right? So now I am just quickly go to you the very brute of this. So the very brute, let's not focus on the entire things. We will just focus on this particular code. I am just going to uncomment this particular code piece, and our is prime should be here only, right? So our is prime is here. So what we are doing in our is prime? So what we are basically doing, if my n, what is the count primes functions is given to us, the n value. If my n is less than 2, then we already discussed the very first prime number start from 0 onwards. So sorry, from 2 onwards. So we are returning 0. Hence we are starting our answer counter, and we are starting iterations from 2 to n. We will search. If self of is prime. So is prime is our method that we just discussed. We have written the exact same game here. So if my is prime is giving you true for this particular number, so we are basically increment our counter and returning final answer here. So what is actually in our is prime? So I have created a function. So this way I would highly suggest to you guys to write your code. So that is the component modularized code. Everything is in a function. So that is a kind of a functional programming. Create your functions and delegate your responsibility of a particular business job you want to run to a particular method. So this method is basically responsible to basically check the is prime things. So how we will basically check? Same logic, divisor count, we are basically start with 0 and we are starting from 1. And how far we will check? We are basically check to square root of n. So my start is basically start from 1, and here we can put square root of my num. So rather than putting square root, so square root is basically a function, right? So if you are putting your square root functions in a boundary, then it is basically going to consume some extra time for you. So that is the most basically intuitive way to write it. So if I can again go to my OneNote, so not on the OneNote, so on that Miro. So what I am basically stating, I have basically put a start variables rather than counter. So now I am basically giving what actually we are basically discussed. So it should run to square root of my num, square root of num plus 1, right? So that we have discussed. So now if I can basically do a like squaring of both the side, right? Squaring of both the side. So now how should it looks like? So I can do a squaring. So start I am basically doing squaring, right? So start I can put a start into start, and on this side it's basically becomes square root of square. So square root and square is going to get cancelled, so it becomes this, right? Now that is our final formula. So that's the reason this square root function is basically going to consume some more runtime. So that's the reasons it is the recommended way to write your things on this term. When you have the square root requirement, do a squaring of your counter variables rather than using the square root functions on your limit. So that's the things we just did here. So you can see we are basically doing start into start less than equals to num. So that is indeed exactly start less than equals to my square root of num. Exactly same things, but it is faster. Now if we are going to check if my nums modulus start is equals to 0, what is my counter here? Start is the counter. So if it is 0, so that means it's the divisor. Now we are going to check if my start equals to nums double divided by start. So if it is a symmetry number, so 25, then 16, so these are 4 cross 4, 5 cross 5, 6 cross 6 is 36. So on that case we are going to consider only a single divisor, right? Because it's first and it's equivalent symmetry, like 5 cross 5. It is a equivalent symmetry, so we should consider it's only one. So that's the reason we need a check. So my start and nums divided by start is equal, then we are going to increase my divisor count to be plus equals to 1, else it is asymmetry divisors we have found. So like 2 cross 9, 3 cross 6 for 18, right? 2 cross 9, 3 cross 6, right? So then on that case we are going to increase my divisor count to be plus equals to 2, and finally my start plus equals to 1, I am doing start plus equals to 1, and if my divisor count is more than 2, returning false, else returning true, right? So that is indeed the brute, right? So now if we can just quickly submit whatever we just prepared. So I am just, for your sake of clarity, I am just going to comment this entire block, and this I don't need to comment because previous of this block executions you guys should aware of this Python doing line by line runtime iterations, right? When the compiler is basically find this return answer, it will not going to execute this line at all, right? So we should be good. Now we can quickly check the correctness of our code. Yes, it's indeed accepted. Now try to submit it. So it is taking a good amount of time for sure, and we are going to get a time limit exceeded for sure, TLE, right? On only 17 number test cases itself, we are going to get a TLE, right? So that's the reasons the very traditional prime number calculations is not going to be help here for sure, because you can see our constraint can be as big as 5 into 10 raised to the power 6, right? So the very traditional way is not going to be help it for sure. So now coming to the actual things that we basically we all are basically looking for. So I can just comment these things out because that is not going to be help a lot. So now basically sieve of Eratosthenes is coming to in picture. So now the sieve of Eratosthenes is coming to in the picture. So now what actually sieve is basically stating, So sieve is on high level, sieve one is high level. So before we start the sieve, so one thing I just going to make you all guys clear. So if you know these things in very basic things, then I will highly suggest to skip that particular part. But I am going to make it very basics in very layman terms, the very in-depth importance of why actually sieve we need. I have already told you guys that I will cover that in very in depth. So that's the reason I will start from like very basic coding, and then we eventually understand the sieve of Eratosthenes whole. So if you understand this, like these basic parts, the prime number calculation, then you can obviously going to skip on your own the particular parts you want to see. But I am basically targeting the audience who are basically very new to basically in this particular coding journey. They can also understand, they should be able to what they basically know what is actually the prime number. But what actually the problems, they are not able to give it a code versions of it. So that's the reason I am basically start from what actually the prime number, then we'll eventually discuss what actually the code versions of its to be look like. So I will basically cover on that iterations only on this particular video. So from very basics we will understand why actually the importance of sieve of Eratosthenes, and eventually we will consume the very at most the complex to complex part we will going to understand for sure. Right? So now focus on the sieve of Eratosthenes. So I am basically give you the high level intuitions what actually the sieve of Eratosthenes basically looks like. So sieve basically stating you, if we have a let me just start with this pencil things, right? Now we need a good understanding things. So sieve is basically stating us if we have a very large boundary altogether. So let's consider we have some dot here, dot here, and this is the last boundary, that is of 5 into 10 raised to the power 6. So it is basically stating us create a very large number list, very large list altogether to your very last boundary that you need to calculate its prime. Right? So our boundary is going to start from 0 to very big as 5 into 10 raised to the power 6. Right? That should be our boundary. Now it is basically how it is basically stating. You can start with marking your all the numbers to be prime. So you have 0, 1, 2, 3, then like the dot, let's suppose it's 8, then 9, then 10, something like this, right? Then we have some dot, and it is going to be 5 into 10 raised to the power 6. So what actually the series basically status, you can start with marking everyone to be prime initially. Focus on these lines, right? Let me just also follow a note also here, because that is if you miss these things, then you are not going to get. So this is actually predefined algo. So here there is no basically, what can I say, exceptions you can state, you can take, you have to understand. So create a list of your extreme boundary. What is our extreme boundary here? It is of 5 into 10 raised to the power 6. Point number two states, mark everyone to be prime initially. Right? I'm giving you the intuitions, guys. Now iterate on your this particular prime list. So if I am going to name it as prime list, where we are, here we are. So if I am going to write it as my prime list, so start iterating from your prime list. But before of iterating, 0 and 1 are they prime? So after marking everyone's to be true, just do a small things. Just mark your prime list of 0 and prime list of 1. Just mark them to be false. Just mark both of them to be false, because that we by number theory we know they are not prime. Now start your iterations from 2 onwards. So start your iterations from 2 onwards for I in range. From 2 to n we are going to iterate. And what we will do, if this particular number so is my prime list, right? So that is my prime list of this particular number I is true, so that means it is true, then we are going to mark its all the multiplier to be non-prime. So what we will do now, we will start another for loop here, another while loop or for loop, whatever you are comfortable with, you can write, and we will start. What is the start of it? It start should be my I plus I, right? So that is my next of its multiplier. So I will iterate my start should be less than equals to my n, and I am going to mark prime list of start. I am going to mark it to be false, because if this is prime, then its multiplier is bound to be not prime, right? Because this number is prime, and its multiplier is bound to get more than two divisor, because it is we are basically deriving this start by doing some multiplications of my I, that is my current prime number. So it is indeed a multiplier of a prime number. So a multiplier, so where we are basically sure we have some, rather than one and that particular number, there is a divisor already belongs, because we are going to its multiplier. So from start, we are going to start from its I plus 1, that is the very start of its multiplier. We'll basically go to its very start prime number, very start multiplier, and we'll mark all of its successive multipliers to be non-prime. So here we are basically doing these things, right? If I am going to complete the next of our line, so if I can go to on this these sections only. So what we can do, then iterate from 2 to n, and if itr, that is my iterables variables is prime, then mark all of its successive multipliers to be non-prime. So that is the games you have to play. And finally, so if you follow these things, your final prime list is basically holding what you are actually looking for. Your prime list basically holding the numbers which is basically prime numbers, it is basically marked by true, and which are not prime is basically marked by false. So that is the intuitions on high levels, but there is a very strong mathematics behind this. So if you going to understand the mathematics, why it is going to be working, so you can create you can take your pen and paper and you can create a very large list, and eventually you will understand it is a kind of intuitive maths, but that is the high levels it is working. So on high levels the intuitions is we are basically starting everyone's to be marking to be prime, and then 0 and 1 we know it is not prime indeed, and we are starting from 2, and what we are doing, if it is prime, then we are going to mark its all of its successive multiplier to be non-prime. So that is the beauty of this particular algorithm. So I am just, for your sake of understanding, I am basically taking one more large number list which we basically able to represent here. I am going to try to take one more large list here. So you guys, I would also highly encourage to you guys to take your list, and you guys also try to understand why actually this particular algo is working. So I'm basically not going to consider 0 and 1, because on 0 and 1 part we are basically doing hard coding, there is nothing to understand, and I am basically start with 2, 3, 4, 5. I am basically trying how big list I can basically able to take, 7, 8, 9, whatever the space permit, I will try to take that big list, 13, 14, 15, 16. So please be there with me guys, because there is a optimization, so you will understand. So that's the reasons I am doing this hard working for you, because there is an optimizations here also, so that I basically try to explain to you. So this you can write, and you will definitely get an accepted for sure, but that is not the Sieve of Eratosthenes most optimized versions, right? So I am basically going to give you the test of most optimized Sieve of Eratosthenes, how it should be looks like. I think I am out of space for sure, 25, 20, 21, 22, 23, 24, 25. So till 25 I think should work for our use case, right? So now let's try to apply our Sieve of Eratosthenes on this. So what we are basically doing, so if my in boundary is, let's suppose 25, so what we are basically doing, from 2 we are jumping to 4, then 6, then 8, then, so it is indeed not a prime, right? 6 is not a prime, 8 is not a prime, 10 is not a prime, 12 is not a prime, right? It is doing the jumping. 14, 16, 18, you guys are getting, right? So we are marking those numbers to be, when we are at 2, so we are basically marking it's all the multipliers to be not prime. Then 20, it's also not prime, right? Because 2 is a prime, so we are going to its multiplier. 22 is also not, 24 is also not. So what happens? So 24 is also not. So now you can see why it is fast. So when you are 3, right? When you are 3, you can start from 3, then you are going to mark to be 6. 6 is already marked, right? 6 is already marked because 6 is marked by 2. So from very early, where we can start? From very early, where we can start? So 2 is prime for sure, 3 is prime for sure. Now where we are getting its next divisors to be marked, where we can first start its next divisor. From 3, ideally we should jump to 6, but 6 is already marked by 2. 6 is already marked by 2. So what is the first naked index we are getting? First naked index for 3 we are getting, it's nothing but 9, right? We are getting to be 9. So here actually the beauty. So from 9 we are going to iterate from plus 3, 9 to 12. So here you can see 12 is also marked. So from 12, what is the index we are getting? 15 we are getting to be play our game. So 9 is unmarked, 15 is also we have done the marking, 15 is also we have done the marking. From 15, 18 is already marked. We are able to mark this 21 by these iterations for sure, right? Then from 21s, are we able to mark anyone? Nope, all are marked. So here you can see we are able to mark only this 9, 15 and 18, sorry, 9, 15 and 21. Then we have this 5. So for 5, ideally we should start from 10. But 10 is already marked. 15 is already marked. 20 is already marked. We are going to mark directly this 25. So from 5, we have a very big jump to be 25. So now the intuitions. So the nested while loops. If this particular I, so we are iterating from 2 to n. We are iterating. So when we are basically studying, if this number is prime. So we are starting our iterations. We are starting our start iterations to be my 2 into I, or you can write it I plus I. Do we need to start from I plus I or 2I? Rather than, can we start to I cross I? Yes, we can start. So that is one major improvement we can write on our nested loops. So we can start to I cross I rather than start to 2I. We can directly start to I cross I. Why it is working? Because the reason is we have already marked some of the child. We have marked for 3. We have already marked this 6. This 6 is going to be marked by 2. So the very first index where 3 is able to do its marking is very start from this 9. Again for this 5, right? It should start from this 10, but 10 is already marked by some of its lowest primes. Some of its lower prime is already marked is very starting index, that is of 2 of this particular I is already marked some of its child primes, or the previous prime. So you can blindly start. So you can blindly skip this 2i's I, thrice I, 4i. You can directly start to be 5i. So 5i is nothing but your I cross I, because you are starting considering your I to be 5. So you can directly start from your I cross I the iteration. So that is the major improvement you can put your nested loop. You can nested loop. Now one more observation. So that is, I think, is very clear to you guys. I basically tried my best to put the very large list to basically give you the intuitions. You should start your nested loop. If it is prime, you don't need to start from 2 I. You can start to be I cross I. That is one very strong observations we have just defined, right? Then we have this for loop. Do we have any optimizations to be placed to this for loop? Do we have any optimizations to be placed to this for loop? Yes. The answer is yes. They are also yes. So what I am stating, you don't need to iterate from 2 to n. I am going to suggest you to iterate to 2 to square root of n. 2 to square root of n. I am basically suggest you to iterate to 2 to square root of n. Now square root we don't use. You guys is already be familiar with this. So we are going to iterate from 2 to, my counter should be, my counter or whatever the variables we are stating, it should iterate from 2 to my counter cross counter, right? When we have square root, we are basically doing its multiplied to my counter. So my counter cross counter should be less than equals to my largest boundary. So that is the boundary conditions we are basically putting to my outer for loop. Now why it is what? Let's understand why. So basically when we have the boundary of 25, we have previously decided we are going to iterate from 2 to 25, right? But now we are going to state we are going to iterate from 2 to square root of 25, which is indeed from 2 to 5. We are basically iterate from 2 to 5. Is this going to work? If this is going to be work, so square root of 25 is coming to be 5. So we are basically going to iterate from 2 to 5. So for 2 we have done the iterations, for 3, 4, 5. So for 5 also we have done the iterations. So I am stating whatever the numbers we currently have at is your actual answer of your 2 to 25 list. 2 to from your n equals to 25 list. Is it indeed correct? Yes. So whoever is the prime, now we have 2, 3, 5, 7, right? 7 is also not marked. 11, then 13 is also there, right? It is also not marked. Then 17, 19, then 23. We have all of our primes in the range of 25 by iterating only for this 2 to 5. Only for these boundary we have iterated, and our nested loops we have started iterating from its I cross I to n, and we got all of our numbers in the list to be marked to be prime are prime and non-prime are marked as non-prime by the very standard sieve algo we just incorporated. So why actually the largest for loops is basically work? Because the reason is the very in-depth maths is basically lie here, guys. So the reason is let's suppose why you guys may ask why man you are not starting from 11. So why it is not making sense to start from 11? Because what is the starting boundary by the brute we defined? It's nothing but 2 into 11, but it is not correct. What is the ideal starting points of a numbers we have decided? It's nothing but I cross I, that is of 11 cross 11. It is already out of boundary. So when you are starting your nested for loop to be I cross I, we are basically starting the numbers we are basically doing some of the intermediate iterations to be skipped and starting from a very targeted index to the end, and like this way when we are marking them all, so we have all the numbers, all the prime numbers to be set within my range. We don't, so for 23 we don't need to start any loop, because 23 is going to be start its first iterations from 23 to 23. It is not going to be making any sense. 19 also. So what is the next very smallest primes we have? This 7s, right? This 7. Why we are not going to start any for loop from this 7? The nested for loops we don't need to check, because 7 is going to start its very start looping from 7 cross 7. It is going to start from 7. It is already out of bound. So we don't need to check any further. So we don't need to iterate our for loop, our outer for loop to be 2 to n. So that is not the correct boundary. So we have defined our outer for loop boundary should be from 2 to, if I am taking it at counter, so it should be square root of my boundary. So we are not taking square root. How we can basically doing The same things we just discussed on our last video. So we are basically doing a multiplication on both the side. So it becomes counter cross counter and it becomes same, right? So that is my outer for loop boundary, and my inner for loop boundary, it should start from my where, if I am going to start, if it is this number is becomes a prime, then we should start our inner for loop boundary to be counter cross counter. So that is my inner for loop boundary, right? So if I can write it inner counter, that is my variables, and we are going to iterate to very big of it. So that is my two for loops boundary, the optimized boundary we have set by this approach, right? By this entire big list we have understand this should be my outer for loop boundary and this should be my inner for loop boundary, right? So the exact same things now I have written on the code iterations. I think I am able to explain to you the sieve of Eratosthenes, very basic, very naive things that we have to follow. The very three basically pillars that we have to follow for the sieve, and eventually the most optimized versions of it also I think is very clear to you guys, right? Very clear to you. I have tried my best, but by any chance if you are not able to understand, I will highly suggest to rewind this particular portion, because this particular portion has the gist of sieve of Eratosthenes. The next part we will do the code iterations. I would highly suggest to go to the code iterations, but before of that, the code iterations, I would highly suggest to try on your own to write, to give it a code versions, because that's how you will basically learn. So I think you guys has already given you that time. Now we can understand our code iteration. So now we are going to uncomment our sieve. So see guys, I am done in a functional programming class, object oriented programming. So I have written it. So I would highly suggest to all of you guys to write it in this object oriented program. So what I have done on our sieve. So first try to understand the sieve, then we eventually understand what actually we have done. So we have initialized our sieve to be, so on the constructor, so that is of def of init, we have initialized our sieve. On sieve, what we actually have at, there is a prime list. So the prime list we are basically marking to be everyone to be true. So one means it's basically prime, one means it's prime. So we are basically marking everyone to be true. So on these lines we basically mark everyone to be true. Then we are hard-codedly mention our 0 and 1 to be not to prime, 0 and 1 to be not to prime. Then we are starting our outer for loop. What is the boundary of our outer for loop? Go to our dashboard, go to our understanding book. Then what is the boundary of my outer for loop? It should start from 2. It should start from my 2 and it should go to my count, my this I cross I should less than my n. If I am making it name this as I, so this should be I cross I should be my less than. But what is the starting? It should start from my 2, right? Am I able to write the exact same things here? Yes, I am starting my I, that is outer for loop, to be 2, and I am writing a while loop. It should iterate from I cross I less than n. Why I put less than n, not less than equals to n? Because here in the problem statement you can see they are basically looking for the number that are strictly less than n. So that is the reasons it's depend on your problem to problem. So that's the reasons I basically put it to be less than n, not less than equals to n, because on the problems we have the very strong lines written here that we should have to see for less than n, not less than equals to n. So that's the reasons less than n. No super magics, no super mathematics. So they have asked us to see for less than n, so we have write it to less than n. Very simple. Now if it is prime, if my self of is of prime, is prime list of I is prime, then we should start a nested loop. What is the starting of my nested loop? Go to our one node. Our nested loop in inner count loop should start from my count cross count. So if I have already mentioned my count as I, so my inner for loop starting should be I cross I. So my j, if I am going to mark my inner for loop to be j, my j should start from I cross I. Is I write the exact same things? My j should start from I cross I, and my j should go to j less than n. Why less than n? Same reason, strictly less than n. So that's the reason I am iterating to less than n, right? And what I am doing, self of is of prime list of j, I am marking to be not prime. We are going to mark it all of its multiplier in the range to be non-prime, and I am going to, what is the next multipliers? It's nothing but of j plus equals to I, same things. Here I think the same games that we have discussed, so we are going to be start plus equals to I. So here my start is basically j, so j plus equals to I, same games that we have discussed, we have written in the code versions of it. And finally after this, if it is not a prime, then we don't have to play our games, we can simply increment our I plus equals to 1 if it is not prime. So not prime, or if it is prime, whatever it is, outer of this my if logic, we have to increment our I to be I plus equals to 1. Right? Like this way, we have our is prime list ready, which is of size of very big. What is the size they are looking for? 5 into 10 raised to the power 6. So we have generated our prime list to be that big. So n you can pass from, so this is parameterized. What if as per your question you can pass your n and you can get an AC. You can basically generate our prime list as per the dynamic requirement. So that's the reason it is object oriented modular code. You can call your sieve of Eratosthenes whatever the ends based on the problem to problem is given to us. We can, the same logic is going to work as it is. The same logic is going to work as it is. So we will solve one more sieve of Eratosthenes, exact sieve of Eratosthenes problems with the same template. You can see what actually the minor changes we have to do. You can going to get the AC. Right? This video can be a little big, so please be in the patience. I am going to upload in non-filtered way. So the main motto, whatever, if I am going to get any runtime or compile time error, you should also you should get the understanding how on the real time I am going to debug it. How on the real time I am going to debug it. So I am going to make it no filter, and the video can be a little bit large, but you will going to get the most of it, most intuitions of the sieve of Eratosthenes for sure. So after watching the entire video, you guys will say me for sure, yes Shavik, I definitely get the sieve of Eratosthenes. I am never going to mess up on any interview. If any problems on sieve of Eratosthenes is thrown to me, I am never going to mess up on this interview. I am become the most powerful candidate of that particular interview for sure. So now I am written one more getter functions, just a getter functions to basically give my prime list to the outer world, to give my prime list to be outer world. So here I am just basically return my is prime list generations after I have done my entire game on the constructor levels on getters. I am just basically vending out. Right. So now my sieve is ready. So now what we can do, we can comment our very brute approach. We can basically comment it out. Right? Now we can call our sieve object. So our sieve object, we are basically calling whatever the n they have given to us on the runtime. So this is not going to be invoked. So it is indeed a dead code because we have commented its caller. So it is not going to be invoked. So this portions I can comment it for your sake of understanding. I can comment these portions, and these portions we just understand now. These portions we just understood. So this is the code currently should looks like, right? This is also a commented code. It is not going to be invoked. So if your guy is going to get confused, I am going to make these portions also to be commented, so that what we have only the gist. So these portions we understood. Now how we have to call it? If my n less than 2, then return 0. There is no prime numbers concept at all. Answer to be 0. Sieve object, I am going to call it to the n value, whatever the n value they are basically looking for. And after we have the object, now can I get my prime list? Yes, call your get is prime list, the getters that we have just exposed, and we get our is prime list. And now how should we have to calculate it? We just need to comment out for I in range n, and if my is prime list is basically giving it to be if in my is prime list it's a prime, then I'm going to increment its count to be answer plus equals to 1, and I am returning my answer. Right. So now quickly just go to the compilations of this code and see the correctness of this code. Yes, it's compiled correctly and giving correct answer on my given test case, and I have submitted it. Let's see. It's taking time. But it's indeed and accepted. It's indeed and accepted. Right. It's indeed and accepted. But it is a kind of a runtime heavy. 2 seconds it took. 2.2 seconds it took. So can we do some more optimizations on it? Some more here and there optimizations. Can we put it? So yes, man, you are not basically used the most of it sieve of Eratosthenes. Why actually we have created the sieve of Eratosthenes? You basically not get the most of it. Why man? Why I am not getting the most of it? The reason is you are basically initializing your sieve of object, sieve of Eratosthenes. You are initializing on test case level. So this function is basically going to be called by test case level. So, but we have already discussed when we have a very large n boundary, we know some of the test case may be asked for 5 into 10 raised to the power 6. Some of the test case may be asked for 2. Some of the test case may be asked for n equals to 2, 15, 17, 25, 100, anything. Some of the test case are going to ask for 5 into 10 raised to the power 6. So rather than going to initialize your sieve object to be test case level, can we make it to be class level? Can we make it to class level? You should not make it to test case levels or the function level. So more appropriate term is function level or the test case levels. We should not initialize sieve at all on any particular interview or any particular contest you are getting sieve of Eratosthenes kind of problems, prime number generations. You should always declare your sieve of Eratosthenes to be class level, Never ever initialize your sieve to be test case levels or functions level. Else you are not going to utilize entire power of sieve of Eratosthenes, because now it is, as it is function level, every functions is basically initialized by sieve of Eratosthenes. So you are not going to get the actual runtime mutations, the power of sieve you are not going to get. So what I am going to do, I am going to just comment this class level declarations, and I am going to go with the function level declarations I have just commented out, and I am going with the class level declarations. Now I am going to initialize my sieve to be 5 into 10 raised to the power 6, 5 into 10 raised to the power 6. So on the class level, what is the maximum boundary my prime list can have it. So that's the things we have discussed in the Miro diagram also. So we are going to initialize our prime list to be class level. The very largest boundary, they are basically people are going to ask, is it a prime? Is it a prime? Is it a prime? We can give it. So what is the largest boundary? 5 into 10 raised to the power 6. So that's the reasons I have initialized to be at 5 into 10 raised to the power 6. So the same things I have just initialized. See what lines I have changed. I have just commented the function level initialization. I have just went with the class level initialization. That's it. Now run it. Is it compiled correctly? Is it still compiling correctly? Yes. Now if I can submit it, previous runtime is 2.2 seconds. Is there any? Yes, man, there are massive improvements. We are getting under 1 seconds. It is 93% faster, almost 94% faster. Previously it's 20% faster. Now its runtime is indeed beats everyone, almost everyone. So it is indeed of 94% faster, right? So that is the beauty of sieve of Eratosthenes. So always declare your sieve functions on class level, never ever on test case levels on function level to get the most power of it. Now you guys should, we are good on this particular question perspective. We are very good, but I am just going to give you a bonus tips. It is a kind of bonus tips, and it is applicable for this particular problem only. Or a large variant of sieve of Eratosthenes problems can be on this board only. So where they are basically asked for the number of prime numbers, that is a count. They are basically looking for the count. Are the count monotonous? Yes, the counts are monotonous. Yes. So when they are looking for count, then can we do a little improvement? Can we use prefix sums? Those who are not able to understand prefix sums, you guys can skip it, but I will highly encourage you guys to basically bother with me with the prefix sum part. We will definitely get this prefix sum versions of it. So on the prefix sum versions, you just have to uncomment this set of lines, what I am basically doing. So if I can again go to my Miro, I can just take your 5 to 10 minutes more to give you the most of it, right? So that if it is a number based prime question, so this is one, right, where they basically interested on the count. They are basically interested on the count. So on the count based problems, this is the 99% cases this optimization should work. So what I am stating, when I have basically creating our prime list, can we create a prefix sum on the same go? So if this is my prime list, and people are basically interested for the count, then I will highly encourage to take a prefix sum, array. It's the name can be very complex. It's prefix sum. There can be many more things, but it is as simple as that case. So 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. This should be more than sufficient. So 2 is prime, 1 is prime. So when we are at 2, we are marking how many what can I say? Tell me how many prime numbers we have encountered ending at index 2. It's 1 because 2 is prime. How many numbers? How many prime numbers we got ending at index 3? It's nothing but, is this particular number is also prime? Yes, 3 is also prime. Then previous prefix sums count, previous index prefix sums count plus equals to 1. So here we are storing 2. 4 is prime, not prime, 0. So whatever the count, what is the count? Till what is the prime number count? till 4 we have. If this particular number is prime, no, it's not prime. So till now we count the number of prime numbers starting from 0 to n is 2 only. That is nothing but 2 and 3. 5 is prime or not? Yes, it's prime. So count plus equals to 1. So till 5, how many? 3. 6, no prime. So count inherited as it is. 7, yes, prime. So count plus equals to 1. 4. So 4 prime. Who are those? 2, 3, 5, 7. Yes, we are getting correct count. So like this way, your prefix sum will work. 4, no prime. So as it is count. 9, no prime. As it is. 10, no prime. As it is. 11, prime. So plus equals to 1. So 5. 12, no prime. As it is, right? So that is the on the same times you can just take a prefix sums, and when this particular index is a prime, whatever the just before of this index, whatever the count, you can take a plus 1 of it, and dump this value to here, dump this value to that prefix sum index. So that's exactly the prefix sum primes should looks like. So here you can see I am iterating for I in range 1 to n, and I am starting with my prefix sums to be 0, and I am amending to my append to my prefix sums of -1, whatever the just of its my previous count, whatever the count is it. If my each prime list is also giving me true, then I am basically taking, if it is 1, then I am basically increment my count to be plus equals to 1, else I am not doing. So you remember, right? Our prime list is basically holding 1 on 0. 1 basically state as it is a prime, and 0 basically state it's not prime. So this prime list, when we are doing plus 1 incrementation, so when it is not a prime, it's by default taking to be plus 0. If it is prime, then it is increments the count and append to my prefix sums, right? So now tell me guys, do we need to iterate now? Do we need to iterate for n? What if on every test case we are iterating to n times, right? We are iterating to n times on my prime list to find till n how many prime numbers are there, rather than iterating. Can I directly return? Can I? We don't need answer also, right? We don't need answer also. If my n is less than equals to 2, return 0. Count is return 0. Same case, base case, right? If it is not, then as the question stated that we have to look for less than n. So we are going to call our prefix sums of n minus 1. So we are going to call our prefix sum of n minus 1, which is basically stored less than n. How many prime numbers we got? Who stored? My prefix sum. My prefix sum basically stored. My prefix sums is stored. That is the extra 2 lines you just have to write. And you can get rid on this function level, test case level iterations also. For every test case, now we are vending our answer to be big of one time. We have just initialized our sieve to be at class level. That is not test case level, it is class level, and we are getting its power to every test case. We are basically able to state how many prime numbers less than my 5 into 10 raised to the power 6, 4 into 10 raised to the power 6, 200, 300. We are going to state its big of one time complexity. We can quickly compile our this particular versions of this particular code and see its correctness. It's indeed correct. And now we have done our submissions. Is it faster? Yes man, it's indeed faster. It's taking 0 millisecond, and we beat everyone, and we beat runtime to be every lead code users with this particular optimizations. With this small observations, small optimizations, we have beat everyone. So that's the beauty, guys. That's the beauty I am basically shared to you guys. So that is the follow-up you are also going to get on your interview. So be prepared in depth of a particular problem. So any variant, any optimizations you have put, any follow-up that you are going to get from your interviewer, you are going to be very good state to handle it. Or I would suggest to you, give the test by on your own to the interviewer, so that there is no chance at all in the world you are going to get rejected on that particular interview. So that's the beauty. We have incorporated the entire intuitions. I have tried my best to I have already sweated out to explain the entire things to you guys. So if you guys are able to understand the entire things, you guys please do a single like. That is going to be help me a lot, and please provide your valuable feedbacks on the comments so that we can do the improvements accordingly, right? So please do. I am trying my best to explain to you guys here, right? So with this, we are good with this particular problems. We can mark this particular row to be done. How we can mark this? Where the color? Yes, here the color. We can mark it to be of color green. Right, so this we have understood. Now there is one more versions I just quickly cover to you guys. I please give me 5 minutes, please give me your rest 5 minutes. We will going to get these particular problems also going to get solved. There is not a single line I am going to write here. I am just use our template. We are going to use our template, right? So this on this particular problems, quickly read the problem statement. Given a positive integer n, calculate and return all the prime numbers less than or equals to n, right? Use the sieve of Eratosthenes algorithms. We will definitely use a prime numbers is a natural numbers greater than 1 that has no positive divisors other than 1 and itself. We know. So for 10, now the problems here you can see it is not less than it. They are basically looking for inclusive our boundary, inclusive our outer boundary. So can we just copy paste our sieve code as it is? Now our prime prefix sums is going to be help or not. Here they are basically looking for count, but they are on this geeks for geeks problems, they are basically looking for the actual prime number. So will these things is going to be help? Prefix sums do we need here? No. Prefix sums only going to be help when we need a count. But here we don't need a count. So we just can snatch our template. We can just snatch our template of our prefix sums, and we have initialized to be class level initialization set done, right? What our n boundary here? 10 raised to the power 4. Now it is inclusive. So to make it inclusive, we know our this sieve of Eratosthenes code we have, the sieve of Eratosthenes code that we have prepared is exclusive, that is of that particular codes. To make it inclusive, what's the changes we have to do? Do we going to change to our template? Do we going to make it less than equals to n, then whatever the other place here also less than equals to n? Nope. We are not going to change anything to our class levels. The class should be as it is. We are going to change in our collar. So we are making our collar to be, we are already making a +1 increment to make it inclusive. We are doing to +1 incrementation from our collar itself, not on the template. We are making our collar to be so that is the modularized code. We are passing the in value here. To make it exclusive, pass the boundary as it is. To make it inclusive, pass +1 to the boundary. So you should be the best person. That is the minor modification based on the problem to problems we have to incorporate. There is no excuse we can put here. Now we have to return a list here, create an answer list here. For iterate now for I in range. From where we should start? From 2. Because 0 and 1 we know it's not prime. How far do we have to iterate? N is inclusive, n plus 1, right? N plus 1. Now if my is prime list of whom I, if it is prime, then I can append answer.append, please append I, that's it. And finally we can return my answer. Finally we can return our answer. Quickly compilation. Yes, we are doing quickly compilation. Yes, it's compiled successfully. Your output 2357, expected output 2357. Quick submit. Yes. It's indeed an easy. All test case pass, and it is taking the optimized versions, because here you can't put the prefix sums because here we are not doing the counter. They basically not interested for count. As straightforward as that, right guys? So with this, we have also done our next problems with the same video we have covered. So this also we can mark it also to be done, right? So this is the two foundational concept of mathematics with the prime numbers. You can get the very hardest versions you can get. We have solved you should be able to solve our template. You should be able to solve the template that we have prepared, right? So I will put the entire templates to this particular video descriptions. You can access that from here. And also with this, I will put the video link here with this video link after uploading completions. We will put this video link here. You can refer these video links any times of the very previous night of your interview. You can just do the very thorough iterations to basically set these things to your brain of your just before day of your interview, right? So with this, we have covered our sieve of Eratosthenes entirely. I guess you guys are able to get the most of it, and if that is so, please guys, please do your valuable comments on the comment section, and please do a single like. That is going to be motivate me a very lot to lot, and please do a comments, your valuable comments. What if you suggest any improvements that we can put, then please do on the comment sections. We'll happily do the changes accordingly, right. So yes guys, so and also please share the videos to your friend circle guys, for sure, and also subscribe to our channel, because from this video onwards I would highly suggest, I have already mentioned on the last video also, because here we are solving the exact highly important interview problems. You should not miss this particular problems at all. So I would highly suggest, please do the subscribe on our channels, and please turn on the notification for sure, so that you can't miss these particular videos, right? So otherwise you will going to miss your interview for sure, right? So that's all about this particular video guys, and if you guys are able to understand all the things, I guess you guys will definitely please do the subscribe, share and like to this particular video. With this I am basically wrapping out this particular video, right? So that's it guys, let's meet with another beautiful question with next video. Bye guys, bye, happy weekend.